Engineers, as we always emphasize, horizontal alignment is ideally the backbone of any road design. So, and when we are talking about horizontal alignment, is basically what you're seeing right now in front of the screen. It is made up of lines, straight sections, curves, and transition curves. And ideally, that is what I want us to go through today, so that you can be able to at least understand the key concepts that you need to have in mind. So in the just concluded session, we have been able to cover the aspect of the design controls that you need to keep in place or in mind as you're doing your design. So ideally, those are broad considerations. And in these considerations, it's important for you to understand that it does not mean that when you consider all of them, there is a guarantee for a balanced design. So it requires you as the engineer to apply a lot of creativity, to be able to be crafty in this craft so that you can come up with a very balanced design. So today, let us go through the specific details that are going to help us to understand horizontal alignment even better and better and better. The first thing that you need to understand is when you're designing a road project, there are some design elements that you need to have in mind when it comes to horizontal alignment. The first one is called the straight. So ideally in this diagram, it is referred as the tangent. It is the straight sections of the road. So this one starts from any project, it must be having some straight sections. And then the second element is the circular curve. And the circular curve is ideally where you can see on my screen right here. And it is defined as the curvature of the road, of course, with a radius. And the radius is finite, means it's limited. It's determined by the design engineer. The second one is for you to transition from a straight section to a circular curve. Quite often you require a smooth transition, and that is why we have the transition curves. And when it comes to many, for example, American text and standards, they call it the spiral. And then that makes a complete curvature of the horizontal alignment of a road. So let's look at this picture. There is the tangent here, and just between the point of curvature, there is where the straight touches the curve. In between here, you're going to have the transition curve, and then you're getting to the curve. And then the same thing happens when you're exiting point of tangency. In between here, you're going to be having a transition curve so that you can go back to the straight section. We'll be seeing the importance of the transition in the next slide. But of course, for you to be able to draw these curves naturally, you require to have tangents. And therefore, the point of intersection, or where these two tangents meet, it's called a point of intersection. And of course, there is an angle of intersection at that point. So for a vehicle to be able to move smoothly and safely in this section, you require to have superelevation, which in simple terms is banking or elevating one edge, mostly the outer edge of the road, to ensure that vehicles do not slide or skid off the road, to ensure that the forces acting on the vehicle as it navigates the curve, it remains on the main carriageway. So those are the main four elements, and that's what we're going to be designing throughout this. So let's go through one or each of these elements. So the first one is the straight, and of course you understand that you cannot be having straights that are infinitely long. So they are controlled, and to you control the length of the straight section, it is tied to the design speed. So ideally, we recommend the length of straights to be a maximum of 20 times the design speed. So if you're having a design speed of 100, you expect to have one continuous straight section of at least 1 kilometer or 1,000 meters. There's also some straights that happen between two circular curves. So it means your section is quite curvaceous, and therefore you'll need a straight section to connect the two. So the reason as to why we need that straight is to avoid what is called the broken back effect. And the broken back effect is, picture it like a camel. So you're having two continuous, you know, and by the one that has double hump or something like that. So for you to be able to drive, it is also your own driving experience. For you to move from one circular curve to another one, if you just have a circular curve and it is moving directly into another circular curve, that's going to be risky for that matter. So you need a longer, comparatively longer section, or a sufficient straight section to help you transition from one circular curve moving in one direction. This one typically, look at your eyebrows. Like it's you moving from the left one is the first circular curve, and the second one is your right hand, the left and the right. So the straight between two circular curves moving in the same direction is ideally like your forehead, or your, is it nose bridge or something, I don't know. And ideally, if you have a short one, you look funny, and if you have excessively long one, again, you look funny. So it needs to be precisely in between there. Okay, so that is just on the light note to demonstrate that. And the risk that are associated with having two long sections is, of course, N-like rare. So it means you're gonna be, in Kenya they call it kuchomana. You're obstructing, the end light is obstructing the driver in the opposite direction, and then of course excessive speeding. People want to move really, really fast at these sections. So ideally, someone would pose the question of what about where the terrain is flat or straight? It means now you need to have speed calming measures. You need also to be warning the motorist through perpetual cues, having speed limit, having speed calming measures along the section to ensure that the vehicles don't overspeed. The second one is the circular curve, and this one is ideally a factor of, or it's influenced by the design speed, and then the maximum super elevation that you're going to have at, and then the side friction coefficient, which of course is determined or dependent on the kind of surfacing that you're going to have. So this means that when you have an extremely, from this formula, when you have very high design speed, we expect the radius to be high, right? And that is obvious. So if the design speed is small, like 20, 30, it means you are going to have a smaller radius. We are seeing that in a few, and you don't really need to do the math and all the calculations, because also the design manuals have at least summarized the major design spins that we're going to be having. And these design spins are of course limited to this maximum super elevation that you have, and in this case we're having a maximum super elevation of 6%. So it is important for you to note that because super elevation is going to affect the radius. You can see it's the denominator. So this means the higher it is, the relationship is right there for you to decode. So there are instances where there is a need to increase the maximum super elevation, ideally sometimes when the curve is pretty tight. So you would want to bank the road at a greater slope, and therefore you can move from 6, sometimes even to 8, and it's being permitted in such instances. But when this increase is effected, it means you need to have a corresponding reduction of the radius by at least 20%. Very important to note. But again, the AASHTO grid book makes it easy for us to be able to see that. So for example, let's look at, for a design speed of let's say 50 kilometers per hour, you can see maximum super elevation is 4%. The limiting values, that is coefficient of friction, is at 0.16, and you can see the minimum, or the radius, the recommended radius is 100. So if you calculate, you're getting 98, and then you are getting 100 when you round it off. So that is what he expects you to work with. But look here, if you increase the super elevation from 4%, let's say, to 8%, you will notice that this is 50, 80, the same constant factor, coefficient of friction, and when you do the math, you're getting 82%. And AASHTO standards recommend that you can be able to work with a rounded radius of 80%. So you can see when you're increasing the super elevation, the banking of the road, it means you have the allowance to reduce the radius. And this is a skill that is mostly used to limit the design parameters, especially where you don't have sufficient parcels of land for you to work with, or probably there's limitation in space. So you would, if the curve is pretty tight, then it means you can increase super elevation at that specific point. That's one. We are done with circular curve. Let's talk about transition curves. So when we're talking about transition curve, is ideally the transition curve is a spiral. It's defined by the equation of a spiral or a clothoid. It is applied to effect the transition between two circular curves or between a circular curve and a straight section. This is very important for comfort, safety, and ease of operation. And the other one is it makes it possible for you to pass from one curve to another, from a curve to a straight, or a straight to a curve with constantly increasing or decreasing centrifugal acceleration. Because ideally, the centrifugal forces will be acting on any vehicle that is negotiating a corner or a curve. So, and these, as you move, it means that the vehicle or the driver will not necessarily be having a constant acceleration or, or a stable. So it means it will be increasing or decreasing, increasing or decreasing. So that is why we need the transition curves. Of course, there are instances that you don't need the transition curves, and mostly when the curve, the radius of the curve is so big, it means that the vehicle can be able, the forces are cancelling out. And then to provide a smooth aesthetic alignment that will blend with the terrain. Look at the picture here, super beautiful, right? You can see the transition from this circular curve here to this other one and to this other. It's super smooth, easy, right? So that is one of it. And then the other one is to accommodate what is called super elevation runoff. So super elevation runoff is ideally the development of super elevation. So this is where the super elevation is starting. So there is the super elevation runoff, and then there is the tangent runout, where the super elevation will be ideally, let's say, where you stop super elevating the section, right? Just for a layman's language. So these are the main important aspects that you need to have in transition curves. And therefore, the transition curves requires keen and careful design, because this also controls the safety. And let us look at another aspect of the transition, and it's called the parameter A. And it's called the Clothoid parameter, the reason being that the transition curve is defined by the Clothoid equation. And this parameter A, this is the formula that you get to see here. Let me just go back. It is a factor of the Clothoid parameter, the radius at the end of the Clothoid, and then the length of the Clothoid curve, or the length of the Clothoid. So this means there are three main considerations of factors that are going to be affected or determined by this parameter A. There's the rate of change of centrifugal acceleration, or the centrifugal force. There is also super elevation runoff. You'll be considering also the aesthetics for that matter. So just to cut the long story short, I'll show you that in the software where we can be able to consider these parameters. But then when you go to the software, you'll find that for you to be able to design an horizontal curve, it will require the tangent on both sides. That's the start and the end. And then it will require the spiral transition, the spiral, or what is called the transition curve, and it will require the radius of the curve. So we've been able to get the radius of the curve from this table or from this AASHTO one. And then after that, the tangent, of course, is the straight section is determined on site. Like you look at the geometry and you decide this looks like a straight section. So you make a judgment on that one. And then the spiral length is, there's a table that gives us the desirable length of spiral curve transitions. And these one, of course, are tied to the design speed that you choose. So for example, for a design speed of 50, you'd require a spiral length of 28 meters. So these factors should be, it should be noted that these factors just but desirable length. But then if you look at it from a practical perspective, 28 meters is so small for you to be able to apply the superelevation on actual site. So 28 is just but the minimums, but if you get to push it a little bit, like 30, 40, 42 changes, all right, or 2 stations is ideally good. Even the operator can be able to, effect transition at that point. So these tables should just be guiding you. These are the minimums, and as you can see, as the speed increases, it means you'll need more transition space for the vehicle to navigate that section. So it's important for you to know that these are just but figures to guide you, but on practical side. But then again, you see, when you're having a design speed of 150, it's something 56 meters, something you can work with. But then again, also if you increase it, it will be better to be applied on site. And then of course we'll be talking about superelevation, and in this case I don't want to talk about superelevation at this point because we are going to have an entire section or session on superelevation. So these are just the guiding principles that are going to help you in the drafting of your horizontal alignment. Please make sure that you pay attention, do it, think through it, try to understand this concept, try to understand the relationship between these. Remember, the design is about putting these pieces together. Like, these are the only design elements. So it's up to you to figure out, how do I arrange them from start to end? So this project is meant to challenge you, is meant to see how much of creativity you can be able to mobilize, if there is such a word, and get to deliver something beautiful and awesome. So I'm wishing you very well as you go through this. Remember, the captains are here to help you. Myself, I'm here to help you. So make sure you at least do a good job so that you push yourself up to where you cannot understand. So if you're stuck at that point, then reach out for help and we'll be here to help you. So cheers, see you around, get to work. Let's see what the future has for us.